This is really one of the best animations for understanding this idea of covalent compound geometry. And so we're just going to go through a couple of examples of each type of geometry. It might be really helpful if you had the Geometries resource guide right in front of you when you go through this presentation, because it'll make a little bit more sense in terms of some of the phrases I'm going to be using. So it turns out there's actually two types of geometry, and you'll see this on your resource guide. One is called electron geometry. That's what comes from being able to count electron clouds. And there are three of them that we're going to be interested in. One is the linear electron pair geometry. One is called trigonal planar. The other one is called tetrahedral. So what we have in front of us is this carbon dioxide molecule that you can rotate around. And one of the things that you'll notice is that when you look at this thing, right, it's just a line. This is a perfect example of the simplest molecular geometry, which is a linear geometry. The important thing to recognize is when you look at the Lewis structure of this thing, that there are two bonds that are connected to the carbon and the oxygen, right? And so here's carbon, there's oxygen, there is the double bond that's between them. There's carbon. There's a double bond between another oxygen and carbon. And one of the things you'll notice about carbon is there's nothing else attached to it. So essentially, these four electrons right here are doing a job holding on to that red sphere, right? That being an oxygen. These four electrons are doing a different job holding on to that oxygen. And so the whole idea of valence shell electron pair repulsion theory is this idea that if you hate your neighbor and somebody stakes you to the ground, right? These guys are kind of stuck to carbon. They don't have any choice but to be associated with carbon here. What's going to happen is you're going to get as far away, as diametrically opposed from each other as you possibly can, right? So there's like a big repulsion between these. If this thing were to bend a little bit, right? So this whole entire bond, if it kind of bent up, that would immediately react by trying to get the hell out of its way. And so you always have what's called this linear electron geometry. And so one great thing is you can click on the button and see an example of what that name actually ends up being. Now, molecular geometry, it turns out it's the exact same thing. For linear geometry, you only have one choice. The second that you're linear, you are an electron geometry that is linear, and you are also a molecular geometry that is linear. Let's move to a molecule that's a little bit more interesting, where these two are actually going to be different. So here's that linear geometry again, right? Let's say that we had a linear geometry. Oops, I didn't realize that would actually, oh, that's kind of fun. Boing! Oh, sorry. So this linear geometry, right, when we rotate it around, you'll notice that there's a bond angle of 180 degrees, which should make sense, right? We are just a line, right? Every line is 180 degrees. So what we're going to do is we're going to add an additional atom to this thing, right? Another charge cloud. Notice what happens the second that I put that charge cloud in there. You'll notice now that when I rotate this thing around, it kind of looks like a propeller. It turns out that anytime you've got this kind of propeller shape, in other words, anytime you've got three electron clouds here, you're said to have an electron pair geometry that is trigonal planar, right? And there's what trigonal planar looks like. Now that we've got a trigonal planar geometry, we can play a few games. It turns out that the molecular geometry, as long as you're bonded to three different atoms and nothing else in the center here, is still trigonal planar, and you'll notice that on your resource guide. If, however, we take this guy away and instead add this thing called the lone pair, you'll notice that we also get that as soon as we add that electron pair, what you'll notice is you still force those down just like you did before, right? These can no longer exist linearly. The weird thing is that as chemists, right, we can only really observe these atoms And these electron pairs right here exert an influence, but it doesn't really appear in the geometry. And so what happens is even though the electron geometry is still trigonal planar, right? We still got 3 charge clouds here. It turns out now we're going to have a molecular geometry that is bent, right? And you can see that this bent geometry is there. If you wanted to click on bond angle, turns out that this is still 1/3 of a circle, right? So a circle being 360 degrees. Now there's a 120 degree bond angle there. But here's an example of something that is bonded to, like a center atom that's bonded to 2 different atoms that has 120 degrees, not 180. Why isn't it 180 like the linear case? Well, it turns out that this lone pair of electrons exerts an influence, and it changes its geometry. Here we are back at our linear geometry. What we're going to do now, we kind of know what happens if we put another electron cloud into this thing and it becomes a trigonal planar. But now we're going to put another 2 in there for a total of 4. And if you're just thinking in kind of flat terms, you're going to actually get the answer wrong, because it turns out that there are 3 dimensions available to this thing. So watch what happens. There's our third. We've become a trigonal planar geometry, right? 120 degree bond angles. And when we stick that 4th electron cloud in there, you'll notice that now what we have is this perfect tetrahedron, right? This is a really popular shape because a lot of things bond to 4 different things, like carbon, for instance. There's a ton of tetrahedral carbons in our bodies. And so you'll notice here that we've got this kind of weirdo bond angle. This is the one that was always really hard to for me to remember, because you can't just like divide up a circle, right? You actually have to think in 3 dimensions. You notice that each one of these is 109.5 degrees. And so this actually has a whole bunch of different possibilities, this electron geometry known as tetrahedral, because now when we consider the actual shape of molecules, we now can replace this group with an electron cloud. We could replace that one with an electron cloud. So let's see what those particular molecular geometries are called by just kind of building them with this thing. And by the way, this is the best way to learn them. I'll have a video where I talk about relating these things a little more specifically to Lewis structures, but to actually see the picture of the thing, it's really helpful to be able to grab it and spin it around. And in class, we'd actually build models of these things, and we'd have a lab where we did that. Here we just kind of have to do the virtual thing. So let's say that I just take off one of those actual atoms and put one lone pair on there. So now you'll see what I have is something that kind of looks like a tripod, right? It's almost like a tripod with a hat. It's all based on the tetrahedral electron geometry. But when we click this box for molecular geometry, you'll notice it's called Trigonal Pyramidal. And that comes from the fact that there's a triangle, a base to this pyramid, right? And so this is called the Trigonal Pyramid or Trigonal Pyramidal geometry. You notice you still got 109.5 degrees in all these things. And now this thing is, you know, it used to just be this nice flat thing before that lone pair of electrons got there. But the second that lone pair of electrons got there, it actually flexed it out of shape. All of these kinds of things are going to become important when you guys get onto like A&P and stuff like that, because it turns out that there's this situation called polarity, where like because of these geometries and different atoms having a different ability to pull on the electrons in their bonds, it actually tends to like separate charges. And so that separation of charge results in these attractions between things, like positives and negatives attracting and things like that, which has all kinds of repercussions for what's attracted to what in a biological system and stuff like that. So that's kind of why we're talking about it now. So what happens if we take away another one of these things and put another lone pair of electrons on there? And what you'll notice is something that kind of looks like Mickey Mouse, right? And this is now called a bent molecular geometry based on a tetrahedral geometry. And you'll notice we still got that 109.5 degree bond angle. Keep in mind that when you look at this thing in like real life, you can't really see these lone pairs of electrons. All you can see are the atoms. And by the way, I say see, but you know, even these things are too small to actually visualize, but they show properties consistent with you know, having some sort of like bent geometry like this. And this is kind of what the picture looks like. So a really typical molecule that's going to have this kind of thing, we'll look at a couple of real molecules and we'll kind of practice naming some of the geometries here. But this is essentially water, right? Water looks like Mickey Mouse to me every time you look at it. Let's spin it around. Ugh, it's a drunken Mickey Mouse. Oh, God. There you go. There's Mickey Mouse, right? Kind of a Mickey Mouse right here. And then I don't know what you want to call this, but that's why H2O has that bend. And one of the reasons that water is so good at dissolving charged things, the reason that we have them in our body, is that this molecular geometry allows it to actually be a polar molecule, which you'll definitely talk a little bit more about in classes like A and P and stuff like that. Also, as a part of this kind of animation, there's this other section that allows you to kind of pick a molecule and practice assigning geometries to this thing. So this is water, obviously, and you can see that water is in fact has kind of like a bend in it. And so you might quiz yourself and say, okay, well, I've got 4 charged clouds. What kind of geometry is this? And you'll say, oh, okay, tetrahedral. And then you can say, well, what is the actual molecular geometry called? And either bent or angular, I think, might be a part of your text. Those both kind of mean the same thing. You can also show bond angles like this, and so you can kind of play around with the bond angles. You can eliminate lone pairs, so you can kind of see what this thing would look like if it was in a particle diagram and kind of floating around with a bunch of its buddies. Right, there's all the little Mickey Mouses there. Notice that those lone pairs of electrons are essentially invisible. So let's look at some other semi-interesting ones. There's CO2, carbon dioxide, right? That guy is actually both linear in molecular geometry and electron geometry. Let's see what else we got on this list. That's a bit of a weird one. Oh, BF3, that's a good one. There's just a straight up trigonal plane. And you could say, okay, what are the bond angles associated with that? Oh, yeah, 120 degrees. So a really helpful thing to look at. There's ammonia. That's probably something you see a lot in like window washing fluid and cleaning solvents and stuff like that. That really nasty smelling weak organic base. And you can also play the game where you say what the heck this thing is, show the bond angles, 109.5. So I'd really suggest you guys check this site out. It's on the University of Colorado site, and it's under chemistry animations, and there is a link to it in the lecture supplements for this lecture, which is lecture number 7. So check out lecture supplement 7 if you want a link to this.